And just start the screen share. And where is the whiteboard? Yeah. So then we can talk on this, right? Okay. So first things first, please tell me that we
Sir,
will solve problems all the time. Yes, yes, please. I have not corrected
sir,
all the
some
answer
of the
sheets. I
marks
have
haven't been
corrected about
released.
half of them. Sorry, फिर से बोलिए.
Yes, sir.
Sorry, आप कुछ कह रहे थे. नहीं, I'm saying I have not corrected all the answer sheets. I have corrected only half of it. I will finish it today. Then I will finish the quizzes today. And as I said, marks are very poor, so we have to do a quiz. I hope I'll try to set a simpler quiz by my standards, but you are not allowed to make silly mistakes. As a matter of fact, all those half answer sheets I have corrected, and all those who have got 2, 3, 4, 5 marks have essentially got a 0. I mean, you have just introduced some concept, or you have simply copied from whatever I have taught without applying your mind at all. Half of you do not know how to calculate Ks and Kp from Haldane equation. That is multiplication division. At least that I had made a mistake not making it. It has to become 5 by 9. And then, of course, the integration becomes irritating. Though one of you had this very clever way of using some online integrator. These are you should not use online integrator. And then, of course, you don't convert from grams to millimoles. So, of course, the answers are completely ridiculous. But that's all right. So, before I start, let us formalize certain things and we will do problems. For example, we will now, please stop me after 40 minutes of class is over and say, sir, now the chance of, please start solving some problems and do some class of problems. So we will spend, I had thought I would cover a large amount of the course. I don't think I will. I will cover it slowly. Some of you said move fast. I think the purpose is to move slowly rather than fast. And so I will give you the quiz marks and this. And now to come to some practical questions. One, the seminar, the term paper. Now the term paper, people keep on asking. I have said it many times verbally, but wow, this is now great. This started right away. Can you hear me and see me? Sorry, can you see the board? So the term paper is of 20 marks.
So we can't see, now we can.
The term paper is of 20 marks. It has to have 4 greater than 4, let us say, type sheets. Type sheets. Well, greater than 3 at least. Greater than equal to 4. Type sheets. In your own words, a summary and a critique, which is a more, I'm deliberately using the word critique, a discussion of the work that you are discussing. It could be immobilization, it could be kinetics, it could be kinetics. I'm writing big terms here. It could be structure function relationships of proteins, structure and function of proteins. It could be structure and function. It could be purification techniques which are best. Not production, production, not production. Production, not production, because that's a different thing. Not production of proteins. No molecular biology, no fermentation technology. It has to be proteins. Okay, it could be in kinetics is the biggest range here. That is what we have been doing. It could be thermodynamics. It could be deactivation. It could be, as we are not going to cover, maybe we won't get the time, algebraic relationships, algebraic models. Can you see?
Yes, we can.
Can you see still? Algebraic models.
Yes, we can.
Multi-substrate models. Okay, deactivation, multi-substrate models. Somebody asked what happens when A and B are there. It is not a simple question to answer. I will try to answer it very, very vaguely. They are called ping pong models and so multi-substrate models. It could be anything. Kinetics is a huge area. And each of you, the idea is to pick up 2 to 3, let us say 2 to 3 papers, preferably old papers, not the new ones. Study what they are saying, old papers, old manuscripts. Go to Google, search out old interesting manuscripts, ping pong model, what is the first paper, what does it say, and then later models, and then discuss it. So you discuss a paper. First summarize what it says, the methodology, and discuss it in your own words. Is it clear? And it is 20 marks typed, and it has to be submitted by 15th of March. So you have very little time. Please go back and do this. And it is 20 marks, and the kind of scores that you people are getting is not very encouraging. So it is also a place where you can score good marks. I am looking at the fact that you have put in an effort and shown some thought. You've given it some thought. In searching a good topic, the topic itself, the search for a good topic itself is an important thing. Do not search a petty topic like purifying using ion exchange. If you look at purification or you look at structure function, pick up something interesting. There has to be some depth in it and some thinking behind it. As I said, a summary of a complex thing and a critique and a discussion. These are the two things. And in your own words. These are the three factors that are important. Plus, of course, the choice of topic, which is left absolutely open. But it has to be on enzymes. It has to be on enzymes. That is all I'm trying to say. Is this argument, is this point clear to all of you? Hello?
Yes, sir.
Yeah, so the second thing that I want to say very quickly is that we have a quiz. We have a quiz, a second quiz, which I hope you score some better marks. I want to try to, it will be a question, one question or maybe two, if it is easy. The second quiz will be one, and I think I'll keep it short, and it will be 10 marks. So please, we will sit down and solve problems now, and that's what you have to tell me all about. And especially when you don't know anything background. And we have a lab quiz as well, a lab mid-semester as well. Now, both these things, and I'm sorry to say, looking at the answer sheets, and this is something which I hope you all realize, have to be offline. So I can hold it on the 14th when all of you have onboarded. If you have onboarded already, I can hold it on the 10th. But I want your class rep or somebody to tell me that, yes, we have all onboarded. If you have not onboarded and you're planning to onboard on 7th or 8th and therefore cannot come on 10th or whatever, then one or two people can do it online. Offline does not mean it is not, it is offline but open book. It is open book and open notes. So you don't have to remember your stuff. But it is important because these, whether it's a lab mid-semester or the quiz, they will be at the most 1 hour. And you will not get a chance to sort of search in Google for an answer. Again, lab mid-semester will be, we'll discuss these questions. Every lab, every quiz, every class, we will discuss problem solving abilities because they seem to be poor. Okay. And you have to read the book that I've given you, Sorrow, Herbert Sorrow. It has some problems in the end of the chapter. They are very simple, childish problems. Doesn't matter. Please solve them. Get a feel of those problems. They will take very quickly. You can run through half the problems and say, I don't even need to solve it. I know how to solve it. But do the other few problems. There is a issue here which needs to be sorted out. Okay, and both these things can be held on the same day. You come to online to a lecture hall, I'll try to block it. Let us block it for 2 hours and I will call your seniors. They will come and finish the lab mid-semester and they will leave and then I'll hand over the quiz and then you can do it. 1 hour each or 45 minutes each and that is it, job done. So you or your class representative give me a date. We will have it offline, open book, both the exams together as early as possible. And definitely not beyond 20th. It makes no sense. Not beyond 20th. It makes no sense because the end semester is sometime in the first week of April. So, you cannot have a midterm in March and then an end semester in, then it's no longer midterm. So I would like to, but I find it extremely difficult to invigilate with all the issues that are very obviously there, not with all of you, but with a small fraction, but it does play havoc with grading and marking. I want it open book. I want it absolutely clear, but I want it offline. And I want a date from you guys by within the next few days, preferably by end of this week. But tomorrow also there is a class, by the way. Tomorrow is also a working day like Tuesday. So tomorrow 9 o'clock we will also have the class. Are this clear? So quiz, lab
Yes,
midterm, quiz is 10 marks, lab midterm is, what is it? 10 marks, isn't it? Or 20? 20. And your end semester is 30 and your lab notebook is 50. So this is lab mid semester 20, end semester 50, this is lab notebook, lab reports is 50 and 30 is end semester. So that is it, and this is important for your seniors who are not here even there, because that's a separate course for them. But this has 1 credit, and this has the course has 3 credits. So I will mark this out of 100. The quiz the mid semester has been marked out of 20. Sorry, the maximum marks written there is 100, but it has been marked out of 20. The mid semester. The quiz will be marked out of 10. So 2 quizzes, 10 each, that is 20, mid semester 20, seminar 20, and end semester 40. And this will be 100. The lab will be marked out of 100, and then we will take a 80-20 ratio of these marks and give you the final grade. Is this all right? I think this has been mentioned earlier. I'm re-saying it again because many of you were not listening. Is it clear how you have to give the seminars, how you have to give the mid semesters, mid-semester, how you have to give the end semester, and when you have to give it? Any more clarifications required in this? Or shall I write it down, or you have heard it out?
it's clear, sir.
It's clear? Thank you. So
yes.
let us now, and please stop me as I said 15-20 minutes, or is it okay? Let us do it the other way around. Let us do it the other way around, because many of you have made such mistakes. First, let's solve a set of problems. Let us solve the simplest set of problems, and then you do the more complex ones. For example, I have an enzyme following Michaelis-Menten kinetics. V is equal to V max S upon Km plus S. Okay, and let us say that these are actually in beads. They have been beads, and I am not talking of, we will talk about immobilization in a short while. And let us say that these beads have incorporated enzyme on them on the surface. And so, as I said, there is no mass transfer for various reasons. We will bring in the mass transfer later. Now, first question number 1. So suppose I know the enzyme loading. Suppose I know the enzyme loading. And the enzyme loading is dependent on, actually remember, molecular weight. You understand? The larger the molecular weight, the larger the loading, because here is the matrix and here is the enzyme being attached on this matrix at this point, and if this is a protein like this, it will attach like this. And remember, there is enough space here because these are one molecule. And if the protein is like this, then it is this. So actually it is the number of molecules which attach per unit surface area. So the higher the molecular weight, the more is the loading. So in terms of, usually therefore people say millimoles. Millimoles is essentially number, remember, by Avogadro number, per centimeter square. Again, per centimeter square. And how do you find out the centimeter square? In say you take beads and you collect the beads in a beaker, and these are fine beads. Remember, these are 200 to 300 microns, not more. Sometimes smaller, sometimes 50 to 100 microns. And I hope you know what a micron is. It's a micrometer. Microns. And suppose I tell you that the bead size is 200 to 300 microns, and suppose I tell you that, let us say some number, I say 1 millimole, or let me put some number 2. Let us say 2 millimoles per centimeter square. And let me say the void volume E is point, usually point. What typical void volumes for circular closed pack systems? Equal size, HCP packing. Can you calculate this for face-centered cubic packing or whatever? You know, you would have done crystallography somewhere. Sometimes you would have touched the crystal structure.
So could you repeat the question?
I am asking you that do you know theoretically how you can find out E for equal size things packed absolutely efficiently? The void volume when things are packed absolutely efficiently. And so on and so forth. They're all equal. And so, oh, sorry. Is there a theoretical way to find out the void volume? Have you learned this? Remember that this is a cube. As I told you, I got 0 marks in my engineering drawing. So obviously these are cubes. Okay.
Yes, so we can count the number of spheres and the volume of each sphere into the number of spheres.
Yeah. So do you know how this is done? How an individual sphere contributes this? How many spheres are contributing? How many touch each other? It's called face-centered cubic and central. And so actually the packing is, I mean, as I said, I'm going far away, but I hope you know these things. I mean, I do not know whether you know these things. So yes, so there is a unit square which is designed based on each. There are cubes which are contributing like this. And I don't know whether you know this. So this is the surface gap. So this is the surface, this is this, and on this is this. I mean, am I making myself clear, or is it very, very bad? Very poor drawing, right? So these are the void volumes. Really poor drawing and messy business. You understand how it is, but you know. So I do not know whether you understood this. These are called BCC models: body-centered cubic, face-centered cubic, and so on and so forth. Hexagonal closed pack. Have you heard of these things ever? Yes, no?
Yes, sir. Yes.
So therefore, what is the typical E that we expect is, well, let us say 0.45 something, or 0.4 or whatever. Let us say something like that. And so if you know E, and I know the micron size, and I know this, now can you tell me how will you calculate the amount of enzyme loading? 200 to 300. Do you need anything else? You need the density. Let us say typical densities of matrices 1.2. Now, please calculate for a diameter range of this 200 to 300 microns and an E value of this and a millimole per centimeter cube loading of this, right? What is the maximum amount of enzyme that I can load? How will you calculate it? Let us have the procedure from you guys. We have to find out the total surface area, right, per centimeter cube, right? Then only we will know that if I take matrix of 1 centimeter. So really what you need to know is amount of millimoles of enzyme loaded, millimoles per centimeter cube, or in 1000 times millimoles per liter, let us say 1 liter of matrix, suppose, or more important, millimeter per centimeter cube. This is what you can measure, or millimoles per gram of matrix, which will just be a matter of. So first things first, what is the surface area of 1 centimeter cube of matrix? What is the surface area of 1 centimeter cube of matrix? In 1 centimeter cube, which is the actual volume, your actual volume is 1 into 1 minus E. Right? Because this is the amount of space left over. So 1 centimeter cube actually has 0.55 centimeter cube of matrix. Is this obvious?
Yes, sir.
Right. So this is one thing. And then you have the volume. And then what is the specific surface area?
So 3 by R if we assume sphere.
3 by R. And that is essentially 3 by R. Oh, I think we should not run.
So 3 by R is Shorter mean radius.
Can you see this screen? Can you, all of you?
Yes.
So
yes,
3
sir.
by R. So 3 by R. No. 3 by R is a shorter mean radius. So between 200 and 300, what would be the shorter mean radius of something which has a size range of 200 to 300? That's a tricky question. It has to be actually integrated, because remember that then you have to integrate number of particles versus radius, and you have to say that let us assume that the particles with radius 200 to 300 has some number distribution, which is something like this, from 200 to 300. 200 this many particles and 300 this many particles. So if you don't know the distribution and then write n is equal to kr, and then you have to integrate, and shorter mean radius will be that r cube upon r square. So it is a tricky business and I will not do this. Go back and sort it out. It will turn out that the mean will not be 250. It will be more like 240 or something, depending on what is the kind of distribution. So if you 240 nanometers, remember that this is microns. So what is the surface area? And let us see, you calculate the units. So let us say, let us say it is 250. So let us say shorter mean R average, SM by definition, is 250 upon 2, right? Because the radius. So let us say, keep it simple, 100 microns or 125 microns. What is wrong? So what is the surface area? Can you tell me? Per centimeter cube? Hello? Yeah, please do it.
So just a second.
Yeah. Surface area, write it out for you. 1 minus E into 3 by R surface area per unit volume. That's it.
So 13.2 centimeters square.
13.2 centimeter. Everybody else got it? Or are you the only person solving it? So this is microns. So I hope you can solve it. 100 microns is, I hope you remember to make it into 100 microns. 100 micron radius is how much in centimeters? It's 0.1 in millimeter, 0.1 millimeter. And so 0.01 centimeter. Right. So please remember your units, right? Of course, this is a very large amount of loading. So, and then 13 centimeters into, so 13 millimolar per centimeter square. And so 13 millimolar per centimeter cube. And then what else do you need to know? What else do you need to know?
So the density of the enzyme per
density, and you also need to know,
density.
you need to know much more importantly the kcat, because Vmax is equal to kcat E naught, and you need to know, so you need to, or K2 E naught as we call it more commonly. Enzyme people call it as kcat. So then if you know kcat and you know E naught, the total amount of enzyme loaded per reactor volume in the CSTR or wherever you are working with, then and only then will you be able to Will you be able to handle the, so in the CSTR, if I say I have added, 1 centimeter cube or 5 centimeter cube or whatever, and then this is really irritating. I've added this much amount and this is going out, and I've added, say 100 centimeter cube of in a 1 liter reactor, then I know the dilution rate, and so this 100 centimeter cube of material that you have added here, this material here which is fixed with enzyme will give you the Vmax as K2 into E naught. Is this clear to all of you?
Yes, sir.
Yeah. So now let us say the case that I take this 100 centimeter cube and pack it into a column. And I know my Km, etc., etc. Now I am asking you that if I flow, and this is the one, let us say this is a, yeah, then the volume is different, right? This is a 100 centimeter because this is packed, so this will be 100 centimeter cube only, 100 ml. And this is the reactor material going out. And suppose I have a CSTR which is, so let me call it, instead of 1 liter, let us say this is 200 ml or whatever. Doesn't really matter whether it's 1 liter or 200 ml. The question really I'm asking you is, I can now take 100 centimeter cube, put it in a CSTR, and I have two questions for you. Let the volume be 1 liter, let the volume be 200 ml. They can all be mixed here in the CSTR. Let us say that I have a flow rate F here, I have a flow rate F here. I can change my CSTR volume given whatever flow rate F. My reaction rate is, I have beads equal to 100 centimeter cube. My question to you is, will volume of 1 liter have a different yield than volume of 200 ml? That is question number 1. Question number 2 is, if this F is equal to, say, whatever, 1 liter per whatever, because I'm not yet giving you the Km and the K2 values. So suppose you know the Vmax and you know the Km values. If given this flow rate and given a substrate concentration SF, and given this flow rate and given a substrate concentration SF, what S out do you expect here? What S out do you expect here? And tell me S out PFR and S out CSTR, which will be lower? What is the sign here? And this is simple Michaelis-Menten kinetics. Hello. Can all of you hear me? Are all of you there? Yeah, some of you are there. Not many. So, bataiye. This is something which would have been answered very easily if you have done a reaction engineering course very well. This is actually basics of it. Bataiye.
Sir, S out PFR would be higher.
Oh. Unfortunately, आपने 50% chance था गलत होने का और आपने कर दिया गलत.
No, sir,
So,
it would be because the average density of this substrate would be higher into the plug flow reactor.
So, think about it. Okay, let us now do it. Let us now do it. Shall I rub this out? जब भी रब आउट करता हूँ सब कुछ उड़ जाता है. So, this is your reaction kinetics. Any reaction kinetics, this is the reaction kinetics V versus S, right? And let us say this is S in, SF, right? And let us for example, let us say this is S out. And let us say this is S out. Can all of you hear me and see me? See the board?
Yes, sir.
So now, in this PFR, of course it will not be horizontal, but I'm just drawing it like this. Here, the concentration is this. here the concentration is this, and here at the outlet the concentration is this. Is this clear? The concentration will fall, yes, because this is a patch going in time, right? And this is the outlet, right?
Yes, sir.
All of you following me? And therefore, yes, the reaction rate here, Rx, is equal to this. The reaction rate here is actually equal to this. And the reaction rate here, I love these colors, is actually equal to this. So the reaction rate falls. So in the PFR, you will have a reaction rate going down continuously from the maximum to the lowest value. If it goes here, then you are in even bigger trouble. In the CSTR, the feed is coming in SF, and can all of you hear me? And this is S out. Hello, can all of you hear me?
Yes, sir.
S out, and this is the reactor, and the substrate concentration is equal to S out because of the logic of the CSTR. And therefore, all the CSTR is at this concentration S out. And so all the reaction is going to take place. This is the CSTR reaction rate. Because D, which is what you have done, in many of you have done, D S naught minus S is equal to Rx, which is equal to V max S out upon Km plus S, which is this reaction rate. So here D S naught minus S, SF minus S is equal to V max S out upon Km plus S out, which is an algebraic equation at the lowest value. In the PFR, it is an integration of the velocity as it moves from here to here. So obviously, you will either need a smaller PFR, or because your reactions are fast, this is faster than this is faster than this, and in the CSTR, only this is the rate of reaction. Therefore, by definition, the conversion rates in a PFR are much more than in a CSTR. It is only when you have zero order kinetics here in this range that the CSTR and the PFR would have the same output. Because zero order kinetics means the reaction rates are all equal in this PFR. The PFR has a continuous declining rate till the end. The CSTR has a rate equal to what it is at the end, because this is all well mixed. And therefore you realize that whenever I have mixing happening in the PFR and this mixes here, in a sense it becomes more like a CSTR, and therefore the more the mixing, the poorer is the yield. The more the axial mixing. So the lower the Peclet number, lower is the yield. Is this argument clear to all of you? So I leave you with a problem, which is solving out this issue of what is the yields for a Michaelis-Menten kinetics. Choose some Km value, choose some enzyme loading, and give me the answers to those two questions. What is the PFR by CSTR yield? What is the efficiency when we load S naught, some SF, choose some velocities, and show me that S out in a PFR is lower than the S out in a CSTR. Because the total reaction rates, this is an integration of the reaction, and this is reaction only at the end point. Can you do this problem? Okay, so I hope you can do this, and I leave this to you as an sort of ungraded assignment. So every class you will do this problem. I will mention the methodology of solving it. I will not solve it. Integration of a standard Michaelis-Menten kinetics, all of you can do, right? And in the CSTR, it's obviously ds naught minus s upon vm s out, km plus s out, which is rather simple algebra. Choose the numbers, find out s out in both cases, and show me what is the efficiency of a PFR by CSTR. And let me ask you this very simple question. This now you can at least answer. As Km increases, does this ratio increase PFR by CSTR or does it go to 1? If you take higher values of Km. Hello? Come on, let us have these are the, as I have written it down, as Km increases, what happens to the output efficiency of PFR by CSTR? You know that PFR by CSTR has an efficiency greater than 1. The yields are better. You know, the productivity of a PFR is higher than that of a CSTR. And let us say in a particular experiment, you find that it is 1.5. Let us say I find that PFR by CSTR efficiency is 1.5. Now suppose my Km doubles. Suppose there is a competitive inhibitor in it. So Km apparent doubles. So as Km increases, the PFR by CSTR efficiency, which was originally 1.5, where will it go? Will it become less than 1.5 or more than 1.5? Again, 50% chance of success, my friends. Hello? Yeah, बताइए. Prashant, you are the only person who is answering. Somebody else, please volunteer, unless you have left and put your face on. Come on, let us have an answer. What would happen as Km increases in an experiment with PFR by CSTR? You did it for a low value of Km. Now you do the same experiment with a high value of Km. And what happens to the PFR CSTR ratio? What happens when, for example, Vmax changes? Vmax doubles, how does this ratio change? PFR by CSTR. Km increases, how does this ratio change? PFR by CSTR. Hello? Any answers? Volunteers? भाई आप लोग 1 2 3 4 5 10-12 लोग तो हैं, मतलब out of a class of 60. So at least 20% attendance or whatever I would like to call it. Out of these 20% people, at least one volunteer to give an answer of what happens to the PFR CSTR efficiency ratios as Km increases. No answers, or think about it. I just now drew this graph. It was I thought it was obvious. Right? Is it not obvious? So this is my Vmax and this is my Km here, and it has now become this, or it has become this, whatever you want to say it. So Km is increasing. Notice that this is the Km value, right?
Yes, sir.
Km is this. So you start here in the SF zone, and if it is low value of Km, and if you stop here, then notice that this is S out, then S out is more or less equal to SF if the Km values are small. So the PFR CSTR efficiency is almost 1. Maybe at the most it's a 1.1 or 1.2 in terms of efficient conversion. But if the Km value is low, notice that the reaction rate has declined this much. And if it is even lower, then it has declined like this much. So as Km increases, then you would more and more prefer the PFR, because as Km increases, your reaction tends to decline faster and faster. So you start at SF. If the Km is high, the reaction is retained at Vmax and it's 0th order. It is 0th order for a long time. So PFR CSTR ratios are 1. The same output. But if it is first order, then PFR CSTR outputs are obviously not 1, because first order integration same time, and first order when the reaction is all in the CSTR, this is the reaction rate. In the CSTR, this is the reaction rate all the time. And in a PFR, the reaction rate goes from here to the minimum value. And the CSTR operates at the minimum value all throughout at the outlet, and the PFR operates from here to here in an integrated fashion. So obviously, if the outlet reaction rate and the inlet reaction rates are equal, then and only then if they're equal, which happens when Km is small, then PFR CSTR is equal to 1. Is this argument clear? Hello?
Yes, sir. Yes, sir.
So these are the things that, I mean, you need to think about a problem. You need to think about a problem because these are things that I sort of avoided teaching completely in my speed to try to rush through. So please solve this problem. Either solve it or you have the analytical and conceptual ability to visualize it without even solving it. Either of the two, right? So now let us sort of, I see this is the problem. When I do this, I lose time. I have to now start. So let me start teaching at the last 5 minutes of the class, right? Next time onwards, we will teach faster. So I was talking about the fact that when you have a bead, you can actually end up having a zone, a diffusive zone around it. And so remember, this is exactly the same problem. So your substrate concentration here may be S0, and you think that the reaction is Vmax S0 upon Km plus S0. That is not true. This is false because the substrate concentration on the surface of the bead is actually S, and what you are having is some kind of film and film diffusive coefficient. You are familiar with this, the film diffusion coefficient. So I'm not going to sort of explain this. You are having the equation Ke, or Ks, let me call it actually, S0 minus S is the rate of diffusion, and that matches with the rate of reaction because you have steady state. I hope you remember. So at steady state, the rate of diffusion of substrate, because this S is at steady state, right? I hope you understand what I mean by steady. This S is obviously changing, but it is the steady state in the sense that when it diffuses from here to here, that is the rate of reaction. Some other S value, the rate of diffusion always matches the rate of reaction, and as S goes down and so on and so forth. So at steady state, you have, and I hope you realize what is the steady state I'm talking about here is not the fact that this is actually not, it is not a CSTR. It may well be a batch reactor. That is why I taught you relaxation times. Vmax S upon Km plus S. So at any given instant, the substrate concentration on the surface is matched by the fact that this is the rate of diffusion and this is the rate of reaction. So these are seconds. These are steady states in seconds, and this is your basic steady state equation by where I say diffusion rate across the film is equal to the reaction rate, right? And I hope you are familiar with, again, the Damp-Polar number. क्या होता है Damp-Polar number in chemical engineering? dA is equal to reaction upon diffusion. Okay, the maximum reaction rate upon the maximum diffusion rate is a measure of the reaction. So it will be equal to the reaction rate, the maximum reaction rate Vmax upon Ks, and maximum reaction is S0. So the Damp-Polar number, which is a ratio of the reaction rate upon the diffusion rate, reaction rate upon diffusion rate, will be given by this number here, diffusion rate. So this is the Damp-Polar number, Vm by Ks by S0, and so we can now use two very simple dimensionless numbers. Later on we might find it very useful. X again as S by S0, S upon S0. So we can dimensionalize this as X goes from 0 to 1, because it can never be higher than. So when is it 1? When is X 1? And when is X 0? When is X 1 and when is X 0? What does it mean when X is 1? What is about the Damp-Polar number when X is 1 and when X is 0?
So when like the conversion is complete.
When X is 1, what does it mean when X is 1? X is 1 means S and S0 are equal, which means diffusion is very fast, right? X is 1 means diffusion rates are very fast. So there is no resistance of the film. Because remember, Ke, I hope you remember this, Ks is nothing but diffusivity upon delta. याद है ना आप लोगों को diffusivity upon delta, where delta is the film thickness and d is the diffusivity, and delta depends on rates of which liquids are flowing, at which the rate at which the liquid, suppose it's a PFR and this is my flow velocity f, then the flow velocity will determine delta and the diffusivity is fixed, so the Ks is determined by f in many ways. Of course, it is not a linear relationship, it turns to change asymptotically. So if f becomes higher and higher, your diffusivity will increase. As diffusivity increases, this number will become smaller and smaller because this is now becoming larger. So this number will become smaller and smaller, right? So your Damn-Kohler number tends to 0. And at Damn-Kohler number tending to 0, X will tend to 1. And it will no longer be diffusion control. It will be controlled by the rate of reaction, because the rate of reaction will now be simply Vmax S naught upon Km plus S naught. Right? So as X tends to 1, Damn-Kohler number tends to 0. It means that there is no diminution. Sorry, the other. What the hell am I saying? Am I saying it right? Does Damp-Kohler number tend to 1 or to infinity? A 0. 0 or infinity? 0 is right. Diffusion rates are very high. So Damp-Kohler number tends to 0. You have X tending to 1. I'm saying it right. Is it all right? All of you clear about this? Hello? Hello?
So could you explain it once again, like why?
Yeah. So what is Damp-Kohler number? Damp-Kohler number is reaction rate by diffusion rate. So what happens, and X, I am defining X as a dimensionless number, S by S naught. Surface concentration upon bulk concentration. That is the surface concentration on the surface divided by concentration in the bulk. One of the reasons I can't explain is this computer keeps tricking me all the time. I think I have to put a complaint. Sorry. So X is S naught by S. I am asking you the question, when does X tend to 1? X tends to 1 when S approaches S naught. S and S naught are the same. When will this approach S approach S naught? When your diffusion rates are high. What happens when diffusion rates are high? When diffusion rates are high, the reaction is controlled by the maximum rate of reaction possible inside, which is Vmax S naught upon Km plus S naught. You can't have a reaction rate faster than Vmax S naught upon Km plus S naught, right? Because the enzyme, and this is S naught here. So the diffusion rates are high, S naught approaches S, the reaction rate approaches Vmax S naught upon Km plus S, Ke into S naught minus S, this number approaches 0. Because there is no difference between the bulk concentration and this concentration that the system sees, because there is no diffusion control, period. So the Damp-Kohler number, obviously given by reaction rate upon this rate, remember Ks is very large, so the denominator goes to infinity, the diffusion rate is very high, and so Damp-Kohler number goes to 0. So a Damp-Kohler number going to 0 really means that the system is running very efficiently without any diffusive controls. Is this argument clear? And X is almost equal to 1. Is this argument clear?
Yes, sir.
So what I'm trying to say is that I can now, so I am writing this now, X is equal to S by S naught, and let me sort of also, and we have already written damp Euler number as, now we will do the algebra a little bit, Vm by Ks S naught, right? Which is a damp Euler number. And we can also define something called kappa. We can define something called kappa, K, kappa as, and that's just making the thing dimensionless, is as Km upon S naught. Just to make this dimensionless. So S by S naught is X. It is a measure of substrate concentration. And kappa is a measure of Km by S naught. You know why I'm doing this, right? You realize that again the same Km will play a huge role. See, this is your enzyme kinetics. This is your S naught. And this is your S. So notice that the reaction rate has fallen from this value here to this value here because of diffusion. But if kappa values were small, then I would have a reaction rate like this and my reaction would not have fallen at all. Even with the same amount of diffusion, I would still not have any drop in the reaction rate because my K values are small. So kappa is a measure of Km. Again, Km plays an important role in determining for how long the system is zeroth order reaction and for how long it is first order. So as long as it is zeroth order, even if I have diffusion limitations, I don't care because my reaction rate should be the same. Are you getting this argument? Or am I just sort of discussing and you are just more comfortable with the algebra?
So it's sort of clear.
Let us write it out. Okay, let me sort of, let us write it out. We are running out of time. Let us not write it out. We will do this next class. I mean, let me sort of wrap up by saying that what is the practical implications of all this? The practical implication is the following, and let me ask you this question again. This is the last question I will ask. So you people just now found out that the volume of the reactor in a PFR can be fixed. So when you go to a plant, you find out what are the bead volume, what are this, etc., etc. So you calculate itna S naught aa raha hai, itna S naught aa raha hai, hame itna S chahiye output mein. This is the desired plant design, and so I can, from my Vmax, Km values, etc., etc., I can calculate volume of reactor. Right? And I can find out. So I know that I need a 10-liter tank. Let us say, I mean, I've calculated volume as 10 liters after all this arithmetic or all this algebra. Now the question is, what kind of 10-liter tank? Should it be, this is also a 10-liter tank. This is also a 10-liter tank. Which one will I choose? One or two? And when will I choose one? When will I choose two? Or why not a tank like this? Or three? They're all one, two, three. This is this. Which one would you choose? And let us end the class at this point. Which tank? All of them are 10 liters. All of them are packed with beads. What is the trade-off that is involved in this tank versus this tank versus this tank? And सब लोग मध्य मार्गी होते हैं गौतम बुद्ध से, लोग कहेंगे बीच वाला चुन लेते हैं. बट बीच वाला कौन सा है? This is a practical question. And you go to an industry, you said, okay, you've done all these studies. How does it help me design a reactor? You've calculated volume, but tell me what is the L by D ratio? That's the question they will ask. Because you know the flow rate. You know the flow rate is 1 liter per minute or volume of 1 liter per minute, 10-liter reactor, etc., etc. Everything is fine. But then, which tank do you choose? Some answers very quickly. And the answer is again that the taller the tank, the higher the delta P. So you cannot keep on choosing taller and taller tanks because your pressure drop is going to become limiting. This is medium delta P, this is low delta P. But your flow rates are high. And if your flow rates are high, in the in the narrower tank, your flow rates are high, your delta becomes small. Therefore, your Ks becomes small because Ks is d upon delta. This is diffusivity. This is damp Polar number. This is diffusivity, right? Upon delta. So delta is a function of flow rate. So as you make that pipe thinner and thinner, your Ks values increase. And if your Ks values increase, your damp Polar number goes down. And therefore your efficiency.
So sorry for interruption. Like we have another lecture.
Yeah, let us finish it here. Yeah, so that is why you please think about what happens with different tanks. Thank you.
Thank you, sir.
Thank you.